Okay, so this is class session 2. We're going to last time we really just got into pandas and just really getting into the Python environment and how to execute code. On Blackboard, I've seen that I've gotten quite a few of the survey responses back from you, so that was very useful to me to get an idea of where everybody's at. I can see that most of you, or all of you, I guess that I've encountered, this is definitely not your first programming language, so that's good. I know a number of you are quite interested in having a chance to work with the Python programming language, and that is very good. If you go into an analytics or a data science direction like me, you will either end up dealing with R or Python. Those are the two big languages in that area. Those are the two big ones. They have a lot of additional packages and other things for this. So this class session, we are going to go over basically neural network basics. So we're going to look at what a neural network is, and this is not a theoretical class, so we're not going to talk a whole lot about how you calculate the output from a neural network or how they're or the inner workings of how they're trained. We could get into gradient descent and stochastic gradient descent and all kinds of fun mathematical theory. That stuff is important, but I'm keeping this class more on the applications of deep learning and how to actually use it. So one thing I do want to go through, just to start with, is the programming assignment is not due next week, but it is due the following week. So if we look at the syllabus, and if I ever forget to magnify one of these, let me know. So basically we got through no class Labor Day. And by the way, I had a really fun Labor Day. I dislocated my thumb trying to do lawn work. So that was not fun. That was... On the plus side, the emergency room only took 15 minutes, so that was good. So I can still type. So Labor Day, we're through that. Tonight we're going over TensorFlow. And then basically to do program 1, all you really need is the stuff in class 1. So to do program 2, which is posted if you want to go look at it, you really don't get enough information until you're up through about class 3. So this is basically, I try to make them do a couple of weeks out from when you have actually all the material. That way if you need to ask me anything. A couple of you, 2 of you to be precise, have already submitted homework 1. So if you do that, I will not actually grade it and send it back to you until after the due date. And by the way, the due date is the day on here at midnight. So you could still, in theory, ask me questions about it on the very day that it's due, and then work on it until midnight after class. So all of 3 hours for that. So that's definitely an option. So let me explain too. What you will get back from me is as far as grading, I am definitely not a nitpicky grader. I'm not going to sit there with this ironclad rubric and literally look for excuses to take points off. I will take points off if you don't have the right output or if the program just fundamentally does not work. If you submit the program to me ahead of time, I probably will take a look at it and see if it works. And if I see something colossally wrong, I will tell you. So that's, if you're concerned of that, submit it early and you'll hear from me. However, while I don't literally look for reasons to take points off, I do give feedback. So what you'll get back at the end of this is you will get my solution. So before I even write up the assignment to it, I create my own solution for it, and I have that ready. That way I make sure that I cover everything that you need to do in order to have that. And then so when I get yours, you'll get the solution, but I will basically print your notepad to a PDF, And I will, with PDF comments, make comments if I do see something that you could do better. So long as your output is correct and your program is doing what I expect. I've had professors literally say, okay, that's the correct output, but you didn't do that the way I would have done that. I really did not like that much, so I would lose points. But that's not how I do that. I grade mainly on just, is it the correct output? And can I tell fundamentally correct output? But I will give you helpful hints because this is a learning experience, and I designed the programs to be very real world, so this is your chance to learn more about how this works. And in case you haven't looked at it yet, program 1, don't freak out and immediately say, okay, it's 7 pages long. What in the heck is this guy thinking? I give you the sample output to it. So the class is how to produce the output. The output is not anything particularly secretive. So I do give you a sample skeleton source file for it. One of the most important things here is the imports. So you can tell basically what packages I referenced for my own solution. So basically the sample skeleton is basically my solution that I wrote, and then I remove all the code that would just completely give it away and make this no fun whatsoever. So you can see that here. So the skeleton is pretty simple, but this gives you an idea right off the bat of what packages I use to actually do that. And then I give you a second listing that shows you my expected output, and I basically explain it. So at the end, you're submitting a zip file that contains the output that these generate, and your output goes into that data file in Data Scientist Workbench. I think I show that in the 5-minute data science workbench tutorial on YouTube, but if I don't, email me and I'd be glad to explain sort of how that works. The output is here, so your output should align to mine. A lot of these algorithms that you deal with, neural networks in particular, are stochastic, so that means that they're random. So you won't always get the same results twice. I try to fix that with seeds as much as possible. But even when you seed a random number generator, as soon as you run something multi-threaded, you have race conditions, and it still won't be exactly the same output. So if you run your neural network a couple of times and it fits, it trains, but you get different results each time, that's what it's supposed to do, because these are random algorithms. Yes. And what I look for typically when I can't exactly look at every single row that you have, so I typically look at, does first row match, does last row, do I have the expected number of rows, and then I look at your code. Does the code produce pretty much what I would expect? One very easy way to end up with the second car as opposed to the first car? Yeah, exactly. 0-based versus 1-based. R is 1-based, so I deal with R all day because that's what other people... So anyway, that's the sample output. The first one just tells you you're calculating the mean, the average. The second one, you're actually calculating a calculated field, so you're calculating the efficiency. Let's see, are you doing that? Oh, you're basically changing some of the values. So the miles per gallon, you're changing that into a z-score. And I have code in the previous class example that shows you how to do that. That's very common. You will see a lot of that tonight. But z-scores are very common in coding for neural networks. Neural networks really like z-scores because they like things centered about 0. This one basically says we basically are going to create a calculated field. This is another very common thing to do in machine learning. So when I give you these assignments, I try very much to pick questions that are real world, that are not just busy work. I want to give, most of these are very much based on actual things that I've had to do quite often. So creating calculated fields, that's very often done because neural networks have certain mathematical abilities. They can't, if you're dealing with underwriting data like I deal with, calculating a BMI might be very beneficial to the neural network. So that's called feature engineering. So here we simply calculate a efficiency that is essentially horsepower divided by displacement, and then you order the cars by that. And Mazda seems to just sort of dominate the first few positions of efficiency. So that's interesting. Not too surprising. And this is 1970s, so most of the American cars are way at the bottom of the list. Question 4 is also very similar to what I do all the time. So you'll have a training and a validation set. So the training set is what you want to teach your neural network on. Now, in assignment 1, you're not creating neural networks because I hadn't taught you them yet. So you're just getting the data ready. So here, literally what you do is you then output it to a file. So you create a file that's very similar to your training data, but you output it so that you have a static version of what the training and the validation data is. Where this fits in the real world is very often we have a team of data scientists working, and we want people using the same training and the same validation. So that final validation, you don't want to just ad hoc divide into 75% training, 25% validation, and have that be a different division every single time you run your program. And also you need to remember on real world data sets, you might be fitting this for a couple of hours. It might be a large data set, you might be running a bunch of neural networks and bagging them together. It just all depends. So you want that to be stable. And that's what we often do at the very beginning is somebody will generate a master file that basically divides the data into training and validation. And we stick to that master file through the whole thing. And it's very important that that's generated with a seed, because as soon as I generate a master file, if somebody says, "Oh, the data have changed. We now need a new." We don't want the training and validation to flip, because then data scientists will have to redo their work. Oh, you mean for the cross validation, the 5-fold. I'll explain. Yeah. So then the next one. So training and validation is one thing. That's where you just take 75% and you set it aside. The problem with training and validation is you train on 75 and you only get accurate predictions on 25%, because you can't trust the neural network to predict on the same data that it was trained on, because it might well have just memorized it. So what you'll do, if you want everything, and we generate these master files too so that everybody's using the same folds, is you take your data, you fold it into 5 pieces. So literally, you then have 5 iterations. So the size of your data set here grows by 5, because now you have 5 distinct data sets. So you have your 5 folds, you pick one of those folds, that's now your validation set for that run, and then the other 4 are your, all concatenated together, are your training set. But that's just the first iteration. The next iteration, so you have 5 iterations, you pick the next fold. And now his neighbor over there that used to be, you always have one that you're using as the validation set, and the other are the training. So basically you create 5 models, 5 neural networks, and we'll see more of this this is a very important concept, so we'll see a lot of this, the cross-validation. And you literally end up with 5 neural networks, and each one was trained on 4/5 of the data and predicted on the other 1/5. So if you take all those 1/5, all your validation, and concatenate them together, you now have out-of-sample predictions for the entire data set. And that's a very useful technique that's used a whole lot, particularly in data science, but artificial intelligence. It's just, what you're really trying to do is say, okay, when I put this model out into the real world, is it going to predict anything like what it did in the lab? So I have a diagram in class 1. We might review that too, just to make sure everybody understands cross-validation, because So what we literally do when we generate the master files is, so all the data scientists are using the same cross-validation, we create, because the idea is now you can have predictions that you trust on the entire data set. So particularly if the data set is small, then cross-validation is very useful. So for question 5, you're basically just generating that as a file. So it'll be 5, so your number of rows should be equal to 5 times the number of rows in the source data set, which is 300 and something, I think, for AutoMPG, almost 400. And then so that's a real quick way that you can check your data to be sure that it's correct, is just to look at row counts. Do you have the number of rows that you expect? Do you have the number of the number of iteration 1s, 2s, and 3s should match exactly the same. It should not be different. And the number of validations, V's, that you have should be 1/5 of the data set. And T's should be 4/5 of the data set. So that's just quick checks that you can make. Okay, back to, so neural network basics. I'm not going to spend a tremendous amount of time on the theory behind neural networks. It's important to some degree. I'm going to show you some of the highlights of it. All the programs that I give you will not necessarily require that you need this. The midterm is going to be primarily, and it's a take-home, it's going to be primarily looking at a Jupyter notebook that I've done to analyze some data, and I'll just ask you some questions about that. So that also will, and I might ask you to make one small change to it to give me some additional information. And I'll probably post that in once we're a couple of weeks, probably 3 weeks out from its due date. So neural networks, basically, one thing that is important about them, very important about them, is their input. So the input to a neural network, essentially what you're doing in all modeling, whether it's a support vector machine or any of these various model types, random forest, gradient boosting machine, you're providing it with a one-dimensional vector that's called the feature vector. And all that these models do is, given this input, either give me a numeric output, which is the regression, so like the car, given these statistics about a car, tell me what the miles per gallon is, or classify it. Classify the car into, I don't know, the station wagon, truck, or van, perhaps. In machine learning, almost all models are one-dimensional feature vectors. Neural networks change that. Most of the neural networks that we will look at in the first half of this class are single one-dimensional feature vectors, just like random forests and support vector machines and all of those. Neural networks, particularly convolutional neural networks, which we'll see in the second half of the class, which are really good for image recognition, they have a 2D, so you can literally send a matrix into it. Or 3D, you can send a hypermatrix into it, a cube essentially. So, or you can even go higher, you can have a hypercube. ND, higher dimension inputs into neural networks are extremely rare. You don't even see that much in academic research. The main difference between 2D and 3D, 2D are used for if you have image input that's black and white. 3D, that third dimension, is your color. And that's the main difference. So for now, we're dealing just with one-dimensional inputs. The word dimension is a little bit unfortunate because there's two uses of the word dimension. You can say, how many dimension is the input vector to the neural network? That's usually what they mean, not what they mean. when they say dimension, because most problems that you will run into, especially in the business world, are 1D vector arrays, single dimension. If you're dealing with images, it's 2 and 3. If you hear about a business problem that's a high dimensionality problem, the cursive dimensionality you might hear of, it just means that your feature vector is really high. So every element in your feature vector can be thought of as a dimension. So it's just two different uses of the same word. This is definitely important. This is true in just about all models. Support vector machines, random forests. It's either classification or regression. What do you want out of your model? Do you want it to tell you a number? Like, and I give an insurance example here. What's the maximum amount that we would insure somebody for? That would be a regression. What's the miles per gallon for a car? That's a regression. Classification is, again, an insurance example. You'll see lots of those from me. Given somebody's age, income, height, weight, HDL, LDL, those are medical calculations that you do on somebody. Actually, those are actual cholesterol levels, and then, yeah, so that's actually not. There is a HDL-LDL ratio that we often calculate. And then it classifies them. Are they preferred risk, standard, substandard, or are we going to tell them no? So that's, and then you have these hidden neurons. Neural networks always have, the layers always have a bias neuron and hidden neurons. That's what they look like. So this is what a neural network looks like. You will see, so this is basically, this is a 2-layer neural network. These were pretty common. Most neural networks were originally a single or 2 hidden layers prior to deep learning. Deep learning, the neural networks are the same. It's just we have very advanced ways to train them. And then there was a famous paper published in, I think, the mid-90s where somebody proved that a single layer neural network is a universal approximator. That means a single layer neural network can learn to approximate any function if it has enough hidden layers. And that was a little bit detrimental to deep learning because you felt like, okay, if a single layer neural network can learn anything, why do deep learning? And why do deep learning? Because the additional layers provide additional layers of abstraction. Just because something can be done in theory doesn't mean it can actually happen. In theory, I could walk home from Washington University to Chesterfield. In reality, I probably wouldn't want to do that. So the additional layers are just tools for the neural network, much like my car, that makes it much more likely that I will actually survive my trip back home. You will also see these bias neurons. Bias neurons they occur usually on every single layer except for the output, and they never receive input. They always output a single value of 1. If you think of the old, like you learned in high school algebra, basically slope-intercept form, think of the weights as slopes. So you have a bunch of slopes because it's high dimension. And think of the bias as the intercept because that's basically what they are. The bias values tell the neural network what happens at 0. And then they all roll up into the output layer, and that's the output. So you have several types of neurons, input neurons. You always have a number of input neurons equal to the feature vector, hidden neurons in between. They're usually in nice layers like this, where you have hidden layer 1, hidden layer 2. And then it all rolls up finally into an output layer. And the output layer doesn't have a bias because what would it feed to? And you notice the bias neurons are not connected, they're output only. And then the neural network calculation is very simple. It's basically X is the input, that's your feature vector initially. And essentially, it's a dot product. It's a summation of all of the i's, where I is the number, where I is the iteration over your number of weights. And usually you treat the biases as part of the input. So you would actually artificially concatenate a 1 here. So your inputs might be 0, 1, and then you would artificially concatenate a 1 for the bias neuron. That's how it's done at the low level. And that's how you calculate it. And it gets passed into a activation function or a transfer function, which we'll see an example of that in a second. In the old days of neural networks, there were all kinds of transfer functions. There was the sigmoid, the logistic, hyperbolic tangent. This is all converged down to basically just one, which is a new one that makes it easy to do deep learning, called the rectified linear unit. If this was a completely theoretical class, I had a class like that. Basically, my midterm, I had to calculate the output for a neural network where he drew all the weights on there, had all the biases. I also had to calculate the weights by hand for this logical expression of A and B, not C or this. And you can do that. You can make the weights up. We're not going to make any weights up by thinking about them. We're going to use computers to train them, because that's all you really do when you really apply these. The only thing that I think is very important about this equation is this is why you often do feature engineering. And feature engineering is where you take that feature vector and you do other types of mathematics and transformations on it, and you create additional columns. That's very important, and that's done very much in the real world. If you look at most neural network examples, you'll see that they just take a data set, they throw some values into it, they calculate the output, and that's just what it is. And we start that way, but then we show it to our boss, the vice president guy, and the senior vice president guys of global R&D. Can you squeeze a little more accuracy out of that? And then we end up doing feature engineering, and that's where you actually do calculations, like you calculate the BMI, or you come up with other transformations that you do on that data that basically alter the search space and make it easier for the neural network to learn something. And Kaggle, where you do competitive data science and people are competing for the top prize to win $100,000 or to win bragging rights to become a Kaggle master. Most interviews with those guys, they say that is where they spend 80% of their time, is engineering that feature vector. And we'll talk some about that. That's an area I'm very interested in. That's actually what my dissertation is about. Mine is using genetic programming to automatically engineer some of those features for you. So why feature engineering actually helps? If you think about the neural network as just this equation over and over and over again, neural networks are really good at multiplying and they're really good at adding and doing that a lot of times. But other mathematical capabilities, if that mathematical capability is important to getting the output to it, the neural network can learn it. But now it's using part of its weight matrix to learn to do a mathematical transformation that you could have perhaps pre-processed for it. So if you're calculating BMI, which is, I forget it exactly, it's height and weight, or 1 squared. So it's a mathematical transformation. There's other biological ratios that are very common. Wind chill, it lets you take temperature and wind speed and result in one number that lets a human being not think about, okay, the wind is this, the temperature, how cold is it going to feel? So those calculations can be very useful to the neural network. And basically it's just doing that weighted sum like I showed you and passing it into the activation function. It's another input, it's a calculated field. So I'll give you one example that I used that was pretty useful of that. Something called a ratio difference is very hard for most models to do. A ratio difference It's not a complicated equation, but it's A minus B over C minus D. So those are 4 inputs. Very simple equation. But most models, if you just take that input, you create 4 columns for those 4 inputs, create random numbers, you can do this in Excel, and create a fifth output where it's just the result of that, A minus B over C minus D. And you give even the most state-of-the-art models that, they will fall apart. They will actually not form a prediction for it. Even though it seems like a relatively simple equation, but try shoehorning that calculation into that, and it gets somewhat difficult. So the neural network won't necessarily learn that. There's a lot of other things that it will learn quite well. It'll learn a logarithm like anything. It'll learn a power like anything. So where I used something of that form, pretty similar, and if you look at my CV online, that's actually a paper I did for IEEE where I looked at a bunch of different forms of equations like that, and I basically created a math test for neural networks and support vector machines, because I wanted to know what mathematical calculations they're good at and what they're bad at to drive my own feature engineering. But that can be useful. So one that I created very similar to that was basically, we were looking at home values, and I ended up doing the price of your house minus the price of the average house on your street, so that's the top part of that. So basically, how expensive is your house compared to your neighbors, and divided by age. And this was basically for input, or for predicting a certain behavior that I shouldn't mention because it's part of our one of our products, but basically looking at how we would predict that. So what that's saying is, okay, how expensive your house is compared to your neighbor, that's a measure of affluence. But then if you divide it by age, older people tend to have more expensive residences on average. So that is an engineered feature that I was able to give to the neural network that had predictive power for this particular case. Now this works for this one, but on a different data set, it might not be all that valuable. But those are the thought processes that you go through when you create these for actual business applications. So you very often use division as a normalizer. So you would do maybe your house divided by the house price of the neighborhood, and that would give you a percent that sort of gave it. Minuses are differences, so you look at the difference between two of the features and then normalize by something. So it's a whole process.
Why wouldn't you just go ahead randomly and do that across all the columns? Create multiple inputs that some will be nonsense, but it should be able to filter those out.
Because that is a very huge number. If you just have, say, 10 inputs, it's not a very large number. But if you, say you have 30, 40, 100, every combination of every feature put into that quickly grows into the billions. So it's, you can calculate it pretty quickly just using the, it's a combination. So it'd be one of those NCR type calculations where you're using factorials in the formula, so it gets big quick. And that's actually part of my dissertation. I get into that and I show several of those where you have just a relatively modest sized 100 and showing literally how that just grows factorially, which is worse than growing exponentially. And I then use a meta-heuristic, and a meta-heuristic is where you don't search the entire search space, you intelligently go through it. So it's a very interesting process, and it's one of the chief things that data scientists do, trying to really represent that data so that the models can do better. Multiplying. So that's very good for fitting certain functions, but other four-dimensional like that can be more difficult. So activation functions, there's all kinds of them. If you Google activation functions, you'll see all sorts of them. This class is dealing not with the history of neural networks, but where they are right now. And where they are right now is there are really only 3 that you will ever deal with. If you look at the most recent research, there are several types of rectified linear unit. There's a leaky rectified linear unit. Don't worry about those. That is absolutely cutting edge at this point. The academics are still hashing out which of those that will be around in a year. But basically, rectified linear units you're going to use for your hidden layers. And then you're going to use either softmax or linear for your output layer, depending on if you are doing classification or regression. If you're using regression, you're going to use linear. If you're going to do classification, you're going to use softmax. And basically, all that softmax does is when you're doing a classification problem, each output from the neural network is one of your classes. So say the iris problem, the iris data set, where you have those 3 types of iris flower. You have the input and you want to know, okay, is it the first iris, the second is, which type of iris is it? Usually you don't just want an output. You don't want it to say, I think it's iris setosa or iris virginica or iris versicolor, the 3 different types of irises in that classic data set. Is everybody familiar with the iris data set? Okay. If not, you will be beat to death with the iris data set in machine learning and AI problems. And why do academics always pick the same darn data sets? You don't have to educate yourself on the data set. If you want to do a classification problem, you're going to do iris. If you want to do a regression, you're probably going to do miles per gallon. If you want to do combinational ordering, traveling salesman. So, and they don't have much imagination. At least that's my problem. So you won't have to think about these too much, really, in TensorFlow, because TensorFlow will pick the activation function for you that you should be using. It's very heavy-handed that way, and it's almost always right. So you're going to you're going to tell it what your hidden layer looks like, and it's going to pick the activation functions for you. There is a way to override that if you really know what you're doing, or you want to, say you're doing research and you want to try a different one of these. And I give you the calculation for the softmax, and essentially and I have a link here to a JavaScript example that I wrote that will do the softmax calculation. All softmax is you have those 3 output neurons. Essentially, whichever one outputs the biggest number is the iris species that the neural network predicted. But usually you don't want that. You want to know what the confidence is. How strongly does the neural network believe in its prediction? Does it believe absolutely, and then the other 2 not so sure? So a classification neural network will always give you a output equal to the number of classes you have. And that number will always be something that adds up to 1.0. So a probability. So if you let me switch to something that zooms. No, I don't have time to set that up. This is what's good about the Notepad, because Jupyter Notepad. So I'm not going to leave this in there, but say you had class A, B, and C, and the neural network was going to predict it. Most likely it would tell you, oh, I think it's class A, I think it's class B, or I think it's class C. Kind of like if I gave you one of those Scantron multiple choice questions and I said, okay, what's the answer? Is it A, B, C, or D? And what do you always do with those type of standardized questions? Well, either you just know it, you know it's A, or you think, okay, C and D, that's just no way. A and B, I'm not so sure about. So then you pick that answer. I mean, I'm sure you've all taken those kind of Scantron ones before. And this is very similar to what you're making the neural network do. You're saying, we have 4 classes. What do you think it is? Is it an A, a B, a C, or D? Maybe like in a handwriting sample. What the neural network will typically, though, do is, and this is what softmax causes to happen, is softmax ensures that these all add up to 1. The neural network will give you something back like this. So that would tell you the neural network is pretty sure, about 90% sure that it's A. Only about 0.6% sure, so not very sure. So this neural network is pretty darn sure that the answer is A. And when you score the neural network, so we'll get more into advanced scoring and evaluation, I think, not next time, but the following. You evaluate, you have to give the neural network some type of score. I almost wish that I could have done this back on standardized exams for me. The way you would score this neural network is say the correct answer was in fact A. The neural network would get 0.9 points. So it wasn't completely sure in its answer, so it doesn't get full points. It gets 0.9. If the correct answer were C, then the neural network took a bath on this particular one. It would get only 0.2 points. So in my example before where I said, okay, I'm pretty sure it's A or B on my GRE exam, but so you can't do this on real exams, but if the exams were any similar to how you score machine learning algorithms, you could say, okay, I'm just going to split it between A and B because I have no idea. It might be A, it might be B, but I'm sure it's C or D. It's not C or D. When your exam was graded, you would only get 0.5 if it was A or B, but you would get no points if it was C or D. And this is how Kaggle is graded. So anyway, that's what the output from neural networks looks like, and that's the output that usually you want to look at with business applications of these. Let's see. So now run those. So anyway, the rectified linear unit, the reason that one is, and the rectified linear unit, what's very interesting about it is so extremely simple. Most of these activation functions have not overly complicated, but relatively complicated formulas that go with them. They're usually trying to be some sort of a S-shaped sort of graph. So the hyperbolic tangent is naturally that way, so it makes a good activation function. But the new rectified linear unit, it's just a max, essentially. It's taking the max of 0 or your x value. So it's a fairly boring looking function, all things considered, but it works extremely well with deep learning. And the reason why, again, I don't want to go too deeply into the theory, but this is what the sigmoid activation function looks like. Essentially, it's a squashing function, so as you're taking those weighted sums, the bigger it gets, it squashes it to 1 or it squashes it to 0. Neural networks are always trained using gradient descent, so you take the partial derivative of one weight with respect to all the other weights, and then the slope, I mean a derivative is the instantaneous rate of change, so to do gradient descent, you actually take the negative of the slope to tell you if you want to go up or down. So say, for example, you were training the neural network and you looked at just one weight and you knew, okay, as I increase that weight, my error tends to go up, 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 and then down, 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 down. And basically, I want to get to the minimum. So if I'm right here, if the weight is currently right here, I take the derivative, which is the instantaneous rate of change, the slope at that point, and that tells me the direction that I need to adjust that weight. And a question might be, well, why don't you just pick the lowest point on the graph? You don't have the graph. This is an extremely expensive graph to produce. Because basically you're saying what is my error, so across all of my data items, what is my error at each of these points on the graph just to get to the lowest point. You only know what your error is at your current weight. So you need to know which way you want to move that weight so that the neural network can home in on a better error rate. And you basically do this process. You take the partial derivative of each weight with respect to all the other weights held constant, and then you adjust each rate scaled by the learning rate, because you don't want too high of a learning rate. If you add too much of it, you'll notice you'll just jump right over that valley and you'll be over here. Fortunately, you'd probably then jump back here and you'd jump back and forth and eventually settle into the bottom. So that's, in a nutshell, how, there's a lot more theory to it, but in a nutshell, that's how neural networks are actually trained. So there's no edge. Weights can be negative, and they can go to negative or positive infinity, and unfortunately, they do sometimes. And once you push one of them to infinity, you end up doing a calculation on an infinity, which becomes not a number, and your whole network's dead. So when you're training and you see it suddenly go to not a number, that means your learning rate, so the step size, is too big. And often they do employ something for neural network training to keep the weights relatively smaller, because you don't need weights necessarily of 10,000. You certainly can. You'll find that all the other weights then are really high numbers just to counter for that. So they'll often do something called regularization, where you try to keep those weights relatively small. We see that actually later as well. And basically this is just showing you, if you take the old sigmoid and you take the derivative of it, it's basically this red one. It saturates to 0 as the x values get large. And that's the entire reason why the ReLU, the rectified linear unit, works a lot better than the sigmoid and all of the other ones, because the derivative of the rectified linear unit is essentially really only two values. It is 1 if it's greater than 0, and it's 0 if it's less than or equal to 0. Now there is a little hand waving here. Technically, the rectified linear unit the derivative is undefined at 0, but the researchers behind this particular one, I think this is one of Geoffrey Hinton's creations. He simply, for simplicity's sake, defines that the derivative of the rectified linear unit is 0 at 0. And it makes the code a lot easier. Now I'll show you one more thing on neural network theory, just why are biases needed. So basically, this chart here, I'm showing you x versus y for just a very simple neural network calculation, which is right here. So this is essentially a single layer of a neural network with a sigmoid function built into it. And I'm showing you what happens if I vary w. So what's the output as I vary the weight? So you'll notice that the input x, that's my feature vector, I get a variety of different outputs, y outputs for this, but you'll notice the different lines, these are just different weights. So as I try different weights, you'll notice it always has to go through 0. This is where the bias is 0. So this is the bias always 0, but I'm altering the weight. So the weight changes the slope of these sigmoid curves. That's primarily what weights do. The bias shifts it. It's setting the intercept. So weights and biases, that's really what they're for. You can do neural networks without biases, but then layers have to, basically the neural network has to engineer its own bias neurons at the hidden layers, and it's in an academic way, it's very interesting to watch it do that. And the first class I was introduced to neural networks, we did something very much like that. But again, I'm trying to keep this more on application than theory. But that's why you need them. They're essentially the intercept. Okay, the next thing is TensorFlow. So this is a good time to take the 10-minute break. If anybody has any questions for me, I would be glad to answer those. But we'll start up again at 7:20. Okay, a couple of things from discussions at break. First of all, if you do download my virtual machine that I mentioned, it does have a password because Ubuntu, there might be a way to do a no password on an Ubuntu login, but the user ID that you log in is student, the password is also student. So it's the same as that. So if you do download my 4 gigabyte, and somebody already has downloaded it and gotten it working, so very, very good on that. And also too, if you want to know literally down to how you would do this on the old-fashioned 4-function multiply, add, divide calculator level, how do you actually train a neural network? On the book's website for volume 3, which I have a link to on the site, but I have a lot of JavaScript that I wrote for various chapters, not all of them, I'm still somewhat filling this in, but if you go to chapter 6, I have basically, and this is all interactive JavaScript that I wrote, you can put any weights that you want to in here, or you can initialize them to random weights. And this is basically a very simple XOR problem neural network. And you can put any input that you want to in there and click calculate, and it'll calculate the output. It shows you the intermediate outputs. And if you want to train it for just one iteration, so just one step, you click that, and it shows you all the calculations that it did for those weights. And it literally shows you almost in just Python type syntax, Java type syntax, that literally we calculated this first sum and it was 1 times that big hairy number, which was a weight probably. And you can literally see exactly, and this is training on a sigmoid function, you can see literally exactly every single calculation that goes into training a neural network. And this is just training an XOR neural network. So this is why neural network researchers really like GPU cards, because it can do this all very fast. Okay, so Google TensorFlow. This is an important command to run. If you run this, it will tell you the version of TensorFlow that you have. 0.8.0 is what IBM Data Scientist Workbench is running. If you download the virtual machine, it's locked to 0.8.0, so you will be in a nice, safe environment. IBM Data Science Workbench is operating on a schedule that is different than Washington University's and mine. So in theory, they could change their version before the end. It won't affect you on Python that much, and I found that the changes are relatively stable when if you So let me just download this one real quick. I just want to show you what that looks like. Download as that. So now I am basically running the latest version of TensorFlow. I'm running on my local machine, on my Mac. Okay, that was just a case of my memory not remembering the right command. So if we look at class 2, and let me zoom this out. So this is now not running on the data scientist workbench. This is running literally on my local machine. So if and I'm sorry if I give anybody motion sickness zipping through this, it's still saying 0.8.0. That's because that's what it was saved to. But if I run it, you'll now see a different number. So you'll see that we're now on 0.10.0, release candidate 0. So this is the latest and greatest as of a few days ago. And if you start to run some of this code, and then you run one where we're actually going to train the neural network, you'll see all these warnings. Just ignore that. That basically is saying that some of these are just warnings. It's stuff that they broke in the process of upgrade, or not broke, but got discombobulated with each other. So if you see warnings come out of TensorFlow in the pink boxes, don't worry about that. If your homework program produces a pink box warning, don't worry about that. If it gives you a big error message with line numbers and stops, worry about that. That's an error. That stopped. But the warnings, unfortunately, state-of-the-art machine learning tends to be a bit chaotic. So every time they upgrade a TensorFlow, I'm keeping a pretty close eye on if the IBM Data Science Workbench upgrades something. So I'll adjust and warn people accordingly. I'm pretty sure we'll make it through the entire semester without them upgrading that, because they have several universities using it. So they tend to upgrade that mid-semester, only not in the middle of the semester. So, but if they do, they're usually not changes that break something. They just start to warn you. Warning, TensorFlow classifier class is deprecated. Please consider using. So this TensorFlow DNN classifier that we're using, it's been renamed to DNN classifier. And as somebody who's written books on these topics, that's really annoying when they do that, but they do it. It's called a breaking change. Fortunately, Google is pretty good about this. They just start throwing ugly messages onto your screen. They don't actually quit working. So TensorFlow, basically, I have some of the links to the install groups. These are some of their competitors. I did post to the forum just literally last week, Baidu, if I'm pronouncing them right, released Paddle. So there is another deep learning framework. It is probably the least mature of all of them in terms of having, it probably works really well for their researchers, but when you unleash the world on it, you tend to have issues that you never even thought of. But it's very interesting. It shows the interest level of the big companies in deep learning, because Google has one, Amazon has one. And basically, I'm not going to go a whole lot into this, but this is basically what something like a TensorFlow is doing. What it's literally creating is a compute graph, very similar to what you deal with Spark. So it literally takes all of those dot products and activation functions and everything. So like this logistic regression node that you see in there, that's actually what they call the softmax function. And then there's this deep neural network, DNN, deep neural network. They've got the training over here. They've got the gradients over here that's resulting sort of from that. You can expand a deep neural network and see the layers. And you can see the individual tensors connecting everything together. This is a toolkit that you can run from the command line. We will not use it in the class. I'm showing you it just literally so that you can see when you talk about the compute graph of TensorFlow, that is literally what it is. But I do give you the command line functions to actually do it if you want to run it from the command line. I've not seen it used a whole lot. I mean, if you're doing research where you're creating your own structure of a network, I suppose it could be used for testing and validation. I'll be honest, I don't know a lot about it. I have not used it much other than to run it and say, oh wow, look, there's my layer 0, there's my layer 1, and there's my layer 2. But the important part of the compute graph is literally what they're doing is they're taking all of your calculations, putting it onto a graph, and then they're literally compiling that. So after you've built your neural network, they literally compile it into really, really optimized C code, C and CUDA code. CUDA is your GPU instruction set, which is also C, C99. And they create this highly optimized representation of your neural network, and that's what runs. So your neural network is not in Python. You're using Python as a glue language to communicate. And there are neural network packages written completely in Python, but they're very slow because Python as a language is just not built to do the heavy-duty lifting of doing all these hundreds, thousands of dot products. Python is very good at calling low-level C, and Fortran too. Fortran is far from dead. It's used for a lot of these analytic libraries. And bringing that data back up into a high-level language that you can deal with, because the C code to some of these models, I've looked at it, it's pretty intense. It's not written for readability. It's written for maximum execution speed. You will hear of something called skflow. That is what we're using. skflow is just a layer on top of TensorFlow. It's built into TensorFlow. It's all TensorFlow. But it makes it a little bit easier to deal with. If you use TensorFlow itself directly, then you have to build the compute graph yourself. And it's not horrible. There's examples of doing that. But for an applications class, and for most things, unless you're trying to create some sort of a custom structure of a neural network, skflow is plenty good enough. It has been built into TensorFlow since 0.8. So it just makes it a lot easier to deal with. Otherwise, you literally have to create the bias neurons and the other neurons and connect them together with a dot product and then create the vector representation of the activation function. And you might find it very interesting if you want to know literally how those low-level calculations work. But for this class, we're just going to stick to skflow. What that means is you may have heard of a library called sklearn, which is a very popular machine learning library for Python. This makes TensorFlow completely compatible with that. So you can literally just plug TensorFlow right into all of the niceties that scikit-learn has. So that is basically what we're going to be using. So throughout this class, I will give you various helpful functions just to try to spare everybody from literally having to build everything from scratch in Python. Most of them are not that complicated. And if you don't, anytime I have a section on helpful functions, these are basically just functions that I have literally taken from my toolkit that I use every day to build up feature vectors and other things for these neural networks. They're not that hard internally, and I will, when we get into pre-processing, which is in 2 classes, I will take you through the inner workings of how all of these do this. But for now, the focus really is on how to use these 4 functions. I think there's 4 of them. Okay, 5 functions to build your feature vector. That's the main idea for tonight, at this stage in the course, is how do you build that feature vector so that you can get it into a neural network, train it, and get a prediction. Another very important thing that I was talking about at class is you'll see these code blocks all throughout a Jupyter notebook. And they may very well have output. This one actually has no output because I'm just defining functions. It's very important that you execute them in the right order if I skip this code block that has these useful functions and I go down a little further and I run something that has those in there, you're going to get an error, undefined function. So make sure you run them in order. I will run this one. It does absolutely nothing visual other than define them. So the little guide as far as what to use them for is here. So basically what you're doing is you're taking this input from either IRIS or from MPG. We're sticking just to those two data sets for now. Believe me, we will actually do more complicated data sets later. But for now, it's good to use the relatively simple data sets just to learn the motions to go through. And this is a big part of data science and artificial intelligence, is building that feature vector. So the 4 values that you have for the irises, they're numeric. Numeric's pretty easy to go in. Numeric is often called continuous, floating point, whatever you want to call that, but the numeric values, you could feed those 4 values right into a modern neural network and not really, it would still predict, it would produce a prediction. You could convert those into z-scores and get a better prediction, because neural networks like numbers that are centered at 0. So those iris measurements, you don't have an iris with a -5 petal width. So they're not centered at 0, they start at 0. So continuous values, you usually want to z-score them, or when we get to pre-processing, there's other options too, but the most common is z-score. If you always want to pick a safe choice for anything we'll do in this class, z-score is a safe choice for numeric values. So you also have to deal with missing values. Feeding a neural network a missing value is about as pleasant as running over a marble with a vacuum cleaner. It's got this nice input that it's expecting, and then there's this not a number or something, and it literally crashes the entire training, because neural networks have absolutely no ability to deal with missing values. So on the predictor side, so for the irises, on those 4 inputs, the way that you deal with missing values, and we'll see more advanced ways to do this, but the most basic way is you fill them in with the median. Always a safe choice. The only time you don't want to is if you have what's called a bimodal distribution, and a normal distribution is just the bell curve. So if I grade all of you guys and I create a nice chart and it's got a bell curve, that's great. If it's a bimodal distribution, that means there's 2 bumps. So sometimes you will actually pick a median from a bigger group. So you might say, okay, I'm going to pick the median from the females if it's a female, that sort of thing. But anyway, for now, for most of what we do in the class, just pick the median for your missing values. Didn't mean to do that, and you'll be fine. So always do that first. If a column has missing values, you can call that on it and they'll be gone. And then for numeric values, you can encode numeric z-score for the predictors. For the output, for the iris, you don't want to, the output is not a number for the iris, but for regression for miles per gallon, you don't need to encode the miles per gallon to a z-score for the output. You could. If you did, it'll be annoying because the predictions from your neural networks will all be z-scores, and you'll have to convert them back. But you can make the output, the neural networks do not particularly benefit from a output being encoded. It's more the predictors. So the numeric values, that will be basically on outputs, and actually on the midterm exam that you will get, which I have not completely built yet, I'm working on it, where you'll analyze something, basically a Jupyter notebook that I worked on. Several of them can all be answered literally right from the text here. So it's encoding the feature vector is very, very important. So that's literally right what that comes from. And make sure you know, predictors, the inputs are handled differently than the outputs. Very important to keep in mind. You don't want to z-score the output because you don't have to. It won't hurt anything. Where it's really important, though, that you treat them differently is categorical values or classes. So the output from the iris is categorical, one of 3 types of iris. So if the input, now if you look at the example or the programming assignment 2, basically what every example of the iris does is they give you these 4 inputs and they tell you to predict the class. I basically flip that around and I say, okay, I'm going to give you 3 inputs to the iris and the class of it predict the petal width or whichever one I picked. So I turn the iris into a classification problem. And it turns out to be an extremely easy problem for the neural network to get. But the test is that can you represent the feature vector? So what you want to make sure you do is realize that iris, okay, when the iris was the output, like it is in a classification problem, like it is almost always, you'll encode it with this function, encode text index. All that does is it says, okay, we have 3 types of iris. And it maps those into 0, 1, and 2. So all of the first type of iris becomes 0. The feature vector has got to be completely numeric. So this is basically just converting everything to numbers. And then for the inputs, so on that homework problem, and I'm giving you part of the solution to it, is when you put those irises into there, now that the iris class has been moved to the input, due to the weird way that I'm looking at that problem, the weird way I make you do that problem, it is now on the prediction side. So you would now encode it with encode text dummy variable. They're called dummy variables. It's from statistics. So essentially what that does is it takes the iris and it blows that field out into 3 fields. So the first field, and those fields, I have an example of it here. So encode text dummies, the 3, say you had red, green, and blue were your 3 classes, it would turn those into 3 different sets of 3 fields. So those 3 fields would be inserted in place of the category that you removed. So you basically call all of these encode functions on your feature vector. It's just a one-by-one process. Take everything and transform it into numeric. You want 100% numeric for your feature vector. Because neural networks can't deal with textual. And there's all sorts of ways to take text into numeric. We're seeing just a few of them tonight. There'll be a few more. We'll probably see maybe like 6 ways total. And these are the functions. So encode text dummies, it's going to does anybody see potentially a problem with this method? So with your classes, what might go wrong with that if you're trying to encode this feature vector? What happens if you have all 50 US states and you treat that as a categorical? How many columns is that going to blow out into? 50. What if you have all the countries of the world? And I don't even know, 400, 300 and something? I don't know that number. But it's several hundred, so that's pretty big. So if you have a high number of categories, this is a problem. And if you have a high number of categories, what do? You sit down and you scratch your head and you try to think of a way to encode those. You might be tempted to just say, okay, we're going to take the states in alphabetical order. Alabama. Is Alabama the first one? I guess. I don't know. But whatever a starting state is the first one to the last one, Wyoming, maybe? 1 to 50, that's a bad idea. It'll typically work, but you're introducing unintended bias. And unintended bias means you're introducing information that is not real. So those numbers, what the neural network would start to lock onto is, okay, Alabama and Arkansas are pretty close together, so they're probably pretty similar states. But Alabama and Wyoming are way far apart, so these are probably very different numbers. So you don't want to do that. If you're encoding like grade school, grades 1 through 8, sure, turn grades 1 through 8 into a number, because that's true. 8th grade is probably more similar to 7th grade, 1st grade is probably more similar to 2nd grade. But if you think, say maybe you think that the state, the main thing that you're getting from the state is the population. Maybe you're modeling something that has to do with, basically with population. Maybe another thing has to do with affluence. I did this with one model and it worked quite well. I picked 4 different statistics that I gathered on each of the 50 states. I think GDP, population, percent rural. I picked 4 different things that I could look up, and I put those 4 numbers in instead of the state. So that's feature engineering. That's how you just wrestle with this. I mean, with countries, you'd almost have to do that, because usually you want your feature vector on a problem like this to be around 100 at the most. So anyway, just make sure you realize if things are numeric or if they're categorical. And then encode text index, this changes them to just, what's good about this is it doesn't, I mean, that's what you don't want to do. This is acceptable to do for the output. So if you were predicting which of 50 states did something, sure, encode it to this. Don't encode it for the output, just like my chart above says. This encodes the z-scores for you. And this encodes, this gets rid of the medians. And then this one is very important. When you're ready to send all of your data to the neural network, you have to send it as basically a matrix for the inputs. So you have a number of rows equal to the number of rows in your data set, just like Excel. And you have a number of columns equal to the number of values that was in your final feature vector. So the iris might just have the 4. So your feature vector, your x is the predictors, would have 4 columns in that matrix. And the iris data set has 150 rows, so you'd have 150 rows. 4 columns. And then you have the y. X and y are usually always separated. Y is just the predictions. So your prediction, your y for the irises would be zeros for the first. It would be the same number of rows, 1 column, and it would basically just tell you what the output is for each of the irises. So this is what it looks like. You'll want the inputs from up there. This is just like class 1, read the inputs. This is important. You'll be creating these for the second program, which again isn't due for quite some time. So we'll see other examples of this again and again. But this is what I do. Basically, these are the 4 fields for the iris. So I basically encode a numeric z-score for that. So when you first get the data frame, the 4 values are all together. The output is there too. So you have 5 columns. Data usually arrives all together. You have the predictors, and then you have the outcome. So we just encode them all together. We leave them all together. They're in that pandas data frame. I'm going to encode this z-score on the sepal length, the sepal width. This is not changing the number of columns at all in my data frame. If I had done a dummy variable, yeah, then it would rip the original one out and put in the 3 values or however many dummy variables you had. And I just encode all of those. And then I encode the index, so encode text index, that is the other, that basically changes the species of flower into 0, 1, 2. And basically this species that it returns, that's my decoder array. So when the neural network predicts, oh, that is species 0, I might want the actual text for that. That's just an array. Element 0 in there would be the first iris. So you don't have to use that if you're perfectly good with just dealing with the numeric output, but that's a quick way to look it up. And when you look at the miles per gallon, it's very similar to this. But basically then I just call X and Y and I say, okay, split this into the X, the predictors, and the Y, the target, or the expected outcome. I tell it the data frame that it comes from, and I tell it that species is what we're trying to predict. And what that will output is you will get a X matrix and a Y array. That the matrix will have the same number of rows as the data set. And that is what TensorFlow wants to train from. That is your pure numeric feature vector. It's not nearly as human readable as the original. We'll see what it looks like. And then you create a deep neural network with 3 hidden layers. Now remember, all the neural network, or all the activation functions and bias neurons and whatnot, this is as deep as you have to go with skFlow. It will figure out the best activation function for you. It's not difficult. It's that chart that I showed you earlier. You just tell it, this is how many neurons I want in each layer. Don't worry about how you pick how many. Just pick something like this. 10, 20, 30 is a good choice often, or usually it's kind of reverse pyramid. You have a lot on your first layer, and then it narrows in, almost like you're narrowing in on decision. We'll learn more about how you pick these. Basically, there's no real good way. It's largely dartboard. You just experiment until something works good. Or you try a lot of values. We'll see how to do that. These IBM Data Science Workbench machines that you have actually have 4 cores available to them. So you can, I'll show you how to literally do a grid search and run a bunch of different combinations all at once and see how that works. That tends to not work as well on TensorFlow. It gets a little, I'm sorry, not on TensorFlow, on IBM Data Science Workbench, but when we get to that, I will show you more about how to do that. And this line, you pass TensorFlow your X and Y, and that fits it. That is where all the weights of the neural network are adjusted. You have to tell it how many classes you have here if it's a classification problem. So there's 3 irises. And steps, that's just how long you want to train it. For now, for most of these introductory ones, 200 or so is plenty good. Later we'll see that we can actually intelligently determine, we can make it stop when it needs to stop. And then it prints a final score. So it basically fits it. And then we basically call classifier. So classifier, that's the actual neural network. Classifier.predict tells it to, I'm sorry, fit tells it to fit it, train it. Classifier.predict, that says, okay, given these same x's, and again, we're keeping it simple for now. We are actually predicting on the same data that we trained on. Normally bad, but to keep it simple for now, we'll get more advanced with that next class. But we're training all 150 values, and then we're going to predict all 150 values, and it does it almost to 100%. Accuracy, I think, is 99%. And then this is an accuracy score. We'll see there's a bunch of ways to evaluate neural networks. We'll look at about 4 of them in this class. Accuracy is the easiest to deal with. It's just like a professor grades an exam. You have 100 questions on it. You missed 3 of them. You have 97%. That's basically what it does. What percent of the irises were classified correctly? So this is a quick way just to do you're passing the prediction into the classifier, or into the accuracy, and then we print out the final score. I have seen many, many examples, and it annoys me to no end, where they basically just say, okay, here's a neural network, we're going to train it, then we're going to figure out its accuracy, and we print out the final score, and they end the program here. They don't show you how to make an actual prediction. Because in the real world, when I create I create a model to predict whether we're going to underwrite somebody or not, my boss doesn't want to know, oh, well, he wants to know what the accuracy is, but when real people use it, they want to make a prediction. So I'm showing you basically how to make a prediction here. We basically, we're going to predict on X, so we're calling those, and then we're going to create a prediction data frame. So we're creating our own data frame, so we're turning those predictions into a data frame, and then I am basically, remember that species lookup table that I had? I'm taking those predictions, because the predictions alone, this is what I'm building, look like this. Predicting, we expected iris is 0, we predicted iris 0. This is a very accurate neural network. And then down here at the end, because it lapses it, we have 2. So I'm adding these 2 columns onto there so that you can actually see how to get the prediction. So I'm basically just looking it up, and then I'm using concat like we used last time, and I'm just concatenating all of these columns together, and I'm building this. And then I just rename all the columns so that they have the nice column heads like I want. Some of these columns already had good names, but I just rename them all too, so that I'm sure. It's easier than having to try to just rename the last few. And when you run this program, when we start to run the more advanced ones, it won't just finish instantly. You'll see step 100, 200, 300, 400, and it'll just keep going. And the final score is 0.99. So it's pretty darn accurate. But we're also evaluating it on the same data that it trained with. And it's also a simple data set. So you will see very high accuracies here. And you can see the feature vector. This is literally the feature vector, like it went into the neural network. So these are all the z-scores. Z-scores are always right around 0, and they don't go very far beyond, say, 2. Because 5 standard deviations would just be an extreme outlier or something such as that. So this is your basic prediction. And all of the questions on the second programming assignment, which isn't due for a while. So when you try these, this gives you plenty of weeks to ask me questions if people are just stumbling over something in Python, because I realize a lot of you are programmers, but Python might be a new programming language. So if you have questions, email is probably the quickest way. Or I monitor my Warshu email at least 1 or 2 times a day. And if you send me a message, I've already responded to several of you on different things. I will typically answer that pretty quickly. Sometimes you might even inspire me to write a little tutorial and put it onto the class website if I feel like it's a common question. So that's where the 5-minute how to install something into, or actually the 2 tutorials that I put online was a result of an email question. So this is how you do a classification. And then I'll show you how to do a regression, and that's mostly it. There's just one other thing, really. Oh, and then I do show you how you can do the predictions one at a time. You don't need to do this for the example, but literally I'm showing you this is how you do it in a loop. Because up here, we just literally shot through it all in vector form. So we had this big matrix, predict on that. Often you might, when you're doing these sort of things in the real world, like for underwriter ratings, I don't necessarily have just a whole big file of it. I'm going to have a bunch of underwriters working cases sending me data one at a time. So in a more realistic application of it, it will probably look something more like this. If you're dealing more with batch data where you just get a big file and you process it, it'll look more like the first one. So this is literally how, if you wanted to just literally put in value by value, unfortunately you do have to reshape it. The reason you have to reshape it is as you get these rows out of the matrix, so it's just row, 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 row as you're predicting them, the input has to be column shaped. So that's the reason we reshape it. And then we just predict them one by one by one. I look up the species name just like before, and that's the output from it. I basically am able to predict those. So if you wanted to predict just one, like if you were designing some sort of API where another application could call you and request just one prediction, that's exactly how you would do it. You wouldn't do a loop, you would do just literally the insides of it. And a completely ad hoc prediction, this, I see very few examples of this, but I do this all the time for real world applications of this when you're trying. So if I wanted to just predict something that's not even in the data set, in academic projects, you get the data set, you fit a neural network to it, you work on some holdback maybe that you had on that, and that's it. You write the paper and it's on its way. I mean, a higher quality one, you might revisit it over and over. But in a business application, you get your initial data, you fit it, and you build this model. But now real world data starts piling in because there was a reason we made this model. It was to predict something that was coming into the business nonstop. And this is more how you do it. So I create a sample iris where I just pick these values off the top of my head and sent it into it, and it says, oh, that weird flower that you just made up looks like it's an Iris virginica. So a lot of these examples, if you just look to the TensorFlow ones, if you look at the TensorFlow examples out on the web, they're fairly academic. They don't really show you how to just take ad hoc values and put those in there. So that's part of what I was working on this summer and continue to work on now, a little bit of, and mainly because I wanted to learn TensorFlow myself really well, but definitely that part about having to reshape the network where you have to take the row and flip it to a column, that was about an hour of head scratching on my part. That was not obvious, and they don't mention that in the TensorFlow manual, unfortunately. But that's what you do. Miles per gallon looks very similar. This is important. Basically the name in the miles per gallon. So if you look at the miles per gallon data set, there's the name of the car. So, and for each of these data sets, I do have each of the data sets that we use in the class. They're all on GitHub. So if you look, datasets MPG, I have a little information page about them, where to download them, the miles per gallon, and then you can see what the data looks like. So this name field, we need to get rid of that. That is useless to the neural network. For one, how would you even encode that? Yeah, and is it even predictive? Now it is actually slightly predictive. You could get a hold of you could figure out, oh, it's a Mazda. So maybe the Mazdas have similar category things. But for the homework assignment, you just drop it. And that is basically what I'm doing there. So I'm just calling pandas and saying drop it. In place is important. You'll see that. One means that I'm dropping a column named name. If I put a 0, it would try to drop a row named name, and that would not work at all. In place means don't create a whole new data frame with that column dropped. Pandas likes to do that. It creates a whole new data frame with whatever transformation. You want to do it in place. You want to lose your original and make the modification. And if you're dealing with big data sets, that's very important. Because otherwise you're just creating duplicate, 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 and you'll run out of memory. And then again, encode numeric z-scores. I'm encoding the horsepower, the weight, the cylinders. Now in program 2, I flip this one just like the iris, and I have you predict how many cylinders a car might have. Turns out to be really easy for the neural network to predict, but based on these other inputs, so we turn the MPG problem, which is normally regression, into classification. And you can use these programs are literally 90% of the starting point for program 2. So I'm teaching you to apply these primarily in this class. If you want to definitely take this to the next level, look at my encode numeric z-score. Try to understand what that's actually doing. Because even if you don't understand how it works and you've made it through it, it might be quite easy for you. They're not overly complicated. But I am going to take you through it line by line when we do the data analysis session. And I always get more benefit from hearing how something works after I've been scratching my head on it for a little bit, trying to see how it works. So I'm trying to kind of give this to you at 2 levels where I will give you these functions. You can use them. And honestly, these are the exact functions I use in my day job to encode stuff. This is it. I mean, this is how you build feature vectors. It's really not any simplified of that. And then if you want to learn it at the deeper level, then you can see how these work. And again, I am basically then encoding it. So I'm encoding it to X and Y. You'll notice here, though, instead of having a classifier, I have a regressor. So that's very important. Use a classifier when you're classifying, a regressor when you're regressing. This is about the range of input or of hidden layers that you'll want. It does take more steps. So if you find you're not getting accuracy of quite what you would want, give it more steps. It'll train on it longer. And then you fit it. You'll see I don't do accuracy on it because you can't do accuracy as easily on the miles per gallon. It's a numeric output. So a very common one, I mean pretty much everything in this class, we're going to either use accuracy or we're going to use RMSE, root mean square. This just says for all the predictions, how many miles per gallon on average was it off by? So you want this number to go to 0, ideally. It won't. You should be concerned if it does. You're probably overfit. But your RMSE will be low, like 3, 4. That means on average it'll be 3 or 4 miles per gallon off. You have to be aware, though, that RMSE is in the same units as what you're predicting. So if you're predicting miles per gallon, being off, having an RMSE of 10 is probably pretty bad because miles per gallons usually go between, I don't know, 10 and 30 or so. So if you're off on average by 10, that's bad. If you're predicting the sale price of a house, 10's not so bad. You're off by 10 bucks. Who cares? So you just need to be aware, RMSE and accuracy, those are our main 2 errors. RMSE is really pretty easy. It's just on average, how many units are you off by? And then basically I do sort of the same thing where I concatenate things together and print it out. So when we run this one, you'll see you have more steps than Iris. So basically it's training, and you'll see the train loss continue to decrease. This should always sort of go down. It might pop up as you go down, but you see it gets lower, lower, lower. So you see why I needed those 5,000 values. And then eventually we hit step 5,000, and here is the output to this. I'm printing out the miles per gallon, the true miles per gallon. This is the feature vector. So this is what it looks like, literally going into the neural network. These are z-scores. Those aren't the real weights. Cars don't typically weigh less than a pound. So that's a z-score. Acceleration, the minus ones just mean lower than average acceleration. On z-scores, the higher this is, these are standard deviations. If you see something like 5 or 4 or even 3, it's probably an outlier. Year, I did not encode to a z-score. It works okay. The main reason I didn't is just so that you could see the difference in this table. Normally I would have possibly encoded it, but... And then origin, I did encode that as a dummy. You'll see the call to dummy above. So you can see that origin basically turned into a dummy. I think 1 is United States, 2 is Europe, 3 is Asia. And that can be very predictive, because especially in the 70s, the Asian cars were the ones that got the really good fuel economy, almost always. So, and this was the predicted miles per gallon, and then the ideal, so the expected. So you can see it's relatively close. It's predicting, it's not dead on, but it's predicting them relatively closely. And all I did to produce that is I basically concatenated them together. I took the data frame, I took the predictions, and then I took the actual, I have a column duplicated now that I think of it. The ideal and the MPG are really the same. I think I wanted them right next to each other just so that you could literally look at them better. Otherwise you'd have to be look 17 and okay, 18. So these two programs are very, very similar. This is really, this is what Python is often used for. It's sort of a glue language where you're basically just gluing things together with it. These are really pretty simple programs. You can see that basically I encoded the text dummy for the origin. All the rest were z-scores. And then I broke it out into X and Y, telling it to use miles per gallon as what we're trying to predict. That just tells it what goes into Y, and it produces the X and Y matrices so that you can feed TensorFlow. And that is pretty much it. That's at its most simple form, classification and regression. And then there's just one last thing I wanted to show you, because again, this is kind of real world. So in the real world, in most demo programs and tutorials you see, you'll train the neural network and then you'll do a bunch of predictions on it. Training models in the real world often takes hours, sometimes less, especially when you're using grids of machines, but you don't want, so if I wrote my underwriter predictor, I don't want to just accept, I don't want to train it when the server boots up just so I have a neural network. I want to save and load it. So that's what I need to do. So this is just the sample code that shows you how to do it. I read the iris data set, I encode it. Basically, I just encode the species. I'm actually getting fairly lazy here. I don't even encode the z-scores. Again, you don't really have to do it. They're numeric. It can deal with it. I split it out to X and Y. I create a classifier. Number of classes 3. I fit the neural network, and I print out the score. And then I save it. And then I set it to none. I've killed the neural network at that point. It's erased. And then I reload it, and I do an accuracy score again. And if I did it right, if it's saved, those two accuracy scores should be exactly the same. So 94%, 94%. So I've saved my neural network, and it's basically there. And I give you the code at the end of the class. I mean, we're really not going to use it, but I want it there just in case you really want to see the compute graph for your neural network. I mean, I basically just show you this is the commands to actually do that. You can't do it in Data Science Workbench, so that's why you don't see one of those generated there. But that is basically how you do that. And that is really all I have for this evening. If there's any questions, I would be glad to answer those. If any of you have any specific like code questions or want me to look at something, I would also be glad to do that individually.